There is no point in rushing forward if actually we haven't mastered the few principles that we have studied so far. So, before we can think of moving to some of the topics that we'll cover, it makes some perfect sense to first just take a quick summary on what we have done under derivatives. So you will notice that we first talked about the first principle, and we said that the first principle is actually used if you wanted to find the slope of the tangent line touching the curve of f of x at point x. So we said that we can actually use this formula here, and this formula is the one that we actually called the first principle. And we have only one thing here, which means that this is actually the first derivative of this function f of x, if there is one here. If there is this one little comma there, if there are two, which means we want to find the second derivative. And sometimes, instead of writing f of x, if let's say we are given some function y is equal to f of x, so we can say that y prime, just y prime with one prime here, is the same as f prime of x. So I want you to get used to this notation here. Y prime is just the same thing as f prime of x, and that is just the first derivative, or the slope of the tangent line that is touching the curve f at point x. And also another notation that is usually used by that was introduced by Leibniz. This one is, we usually say dy dx. This is still the same thing as that, and this is the same thing as that. But what is important here, I want you to know that this equation here is the first principle. And we said that if let's say you have a function and that function is equal to some constant c, the constant can be 1, can be 5, can be 10, can be root 2, can be anything, as long as this one is a constant, its derivative, or the first derivative, is always going to be a 0. That's what we said last time. And then we started to talk about the derivative of a power function, and we said that derivative, that rule is a power rule. So if we have a power function, we have an independent variable raised to some real number there, then the derivative of that particular function, we always get it by just bringing in the exponent down, this real number here, and then we keep the x, and then we subtract 1 in the exponent. That's what we said it is a power rule. And then we talked about having a function multiplied by a constant. So if you have a function, let's say our function is h of x, and we are multiplying, this is the same as f of x times some constant c, whereby this c is a real number. It can be negative, it can be positive, it can be a decimal, it can be anything, as long as it is a real number. Then h prime of x is going to be always, we pull out the constant. As you can see here, you can always pull the constant in front of the derivative and take the derivative of the function here, which means that our h prime of x is going to be c times f prime of x. Take note that keep taking this summary down, just in case you might have missed something that we did. And then we also talked about the sum rule, whereby we have two functions, f of x and g of x, and if this function and that function, they are both differentiable, in other words, the derivative at any point, if let's say the point x is still within the domain of the derivative of this, and also the domain of the derivative of this particular function, we can always find the derivative of the addition or the sum of these two functions by just taking the derivative of f of x and then take the derivative of f of x, and then take the derivative of g of x, and then we can just add them. So that's what the sum rule was actually saying. As long as you know this function and that function are differentiable, then just take the derivative of this and the derivative of that, and then you sum them up if you want the derivative of the sum of the two functions. The same thing when it comes to the difference between two functions. All you need to do, take the derivative of f of x and take the derivative of g of x, and then you just take the difference, or you just subtract the derivative of this from the derivative of that, and that is what we call the difference rule. And if you are looking for more examples on this, we already have a lecture that is actually aligned with those rules. I think it was supposed to be lecture 34. I think it was lecture 34 that is actually considering these rules, except for the first one, which was the first principle. The first principle is in lecture 33, which is introduction to derivatives. And then we talked about the product rule, and we said that if we have a function f of x and g of x, and both of these two functions are differentiable at point x, then to find the derivative of the product of these two functions, all you need to do, first keep this function g of x, which is the second one, and then you take the derivative of the first function, which is that, you multiply them, and then you add, you keep the first function, and then you take the derivative of the second, you multiply them, then the sum of these two products is actually going to be the derivative of the product of these two functions. And take note into this that we actually having this. Now there is a plus here when we're actually considering the product, but when we are considering now the division, so we have two functions and now want to find the derivative of these two functions, you will actually find out that we still follow the same thing here. The second function here it is in the denominator, so we keep the denominator as it is, and then we multiply by the derivative of the numerator, and then we subtract. Division means we subtract, and then we keep the function in the numerator, and then we multiply by the derivative of the denominator. Because there is a denominator there, it turns out that actually we will have to divide by the denominator squared. Of course, these things, they can always be proved. For now, we want you to know how to actually use these product rules. If you want to prove them, there is no problem with that. You can always try and dig further to actually prove these things. But for you, we want you to actually focus for now with using these rules as they are. If you are struggling to actually remember this rule, we can always say that, of course, other people are using different things. We can always say low, which means that the function in the denominator, d, which means the derivative, and then high, which means the numerator. You can always think of low d high minus high d low divided by low low, just to know that in the denominator we have a square, which means the function times that function. So this is one way of remembering this rule here. And then we talked about the chain rule, and then we said that if you have a composite function, in other words, you have h of x, and then this h of x is equal to f of g of x. If you want to find the derivative of this particular function, all you need to do, you need to take the derivative of the outside function with respect to what is inside, and then you multiply by the derivative of what is inside now with respect to x. And of course, it's very normal to think that actually this does not really make any more sense when we're actually speaking in terms of derivative, especially if you're looking at it for the first time. Yes, as you becoming you practicing and you understanding the composite functions, this will make a perfect sense. But in most cases, when you're still doing chain rule for the first time, this does not usually make sense, and most students usually prefer this one because it makes so much sense to them. So if you wanted to find the derivative of this function here, the first thing that you need to do here, you let this inside function, which is g of x, to be equal to some u. So you let your u equal to g of x, and then you let your y, once you have this as your u, you replace this g of x by u. As you can see here, I replace g of x by u, and then the function that I actually get now, I let it to be equal to y. So y is equal to f of u. Then once I have that, I can say that the derivative of h of x is going to be dy dx. You can see that y is still the same function because this u is that g of x, so I can say that h prime of x is going to be dy dx. But now when I'm looking at y, my function y here, it is in terms of u, not x. So if I really wanted to find its derivative, I have to find it with respect to the variable u. And then once I have done that, because it was not part of this, I still have to cancel it out some way, in some sense. We are cancelling it out by saying that we have du dx. I want you to think like that actually think of this as some sort of cancelling this thing out, even though that is not the case. But if you think it like that, you will start to see now that actually I have this dy divided by dx, and this is what we call the chain rule. And then we used these rules above to actually prove that the derivative of sine of x is the same as cosine of x, and the derivative of cosine of x is the same as minus sine of x, and the derivative. So this one and that one, we used the first principle to actually prove these two. And then when it comes to c, we actually started to use, because this one is sine divided by cosine of x, we used what we call the quotient rule to prove that actually tan of x, the derivative of tan of x is the same as secant squared of x, and the derivative of cot of x is the same as minus cosecant squared of x, and the derivative of cosecant x is the same as minus, can you see that we have a cosecant x, so cosecant x is still supposed to be there. And then now if you look at the cosecant x, you can see that cot still have cosecant x, which means now the derivative of this ended up becoming this nice function here, which is cot x minus, we have a minus here, cot x and cosecant x. Take note that when we are dealing with cot and cosecant, we have a minus there. And now when we are actually dealing with the secant x, you can see that okay, tan of x is secant squared x, therefore the derivative of sec x is going to be tan x and times sec x. Here we have a positive sign. It's only cot and cosecant that actually have a negative sign, so we have this nice thing. And then after doing this, these rules here, the rules that we're actually using, we're using the quotient rule and the chain rule to prove these nice things here at the end. But the first two, we're using the first principle. And then when it comes, if you wanted to find out how we actually did this, you can check lecture, I think it was lecture 36, which was the derivative of trigonometric functions. And then we moved and we find out the derivative of e to the power x is the same as e to the power x, and we used actually here the first principle, which was actually and also we used the knowledge that the limit as x approaches 0 of e to the power x minus 1 over x was equal to a 1. We used this to actually prove this. And then here we just changed this to have an e, and then we started to use chain rule, and then we ended up proving that actually the derivative of the exponential function a to the power x is the same as a to the power x times ln of this constant a. And of course, if you are using this, you can see that if a was e, here you'll end up having ln e, and ln e is the same as 1, so you end up getting something of that nature. And then the derivative of log base a of x, we found out that this is the same as 1 over x times ln of a. And of course, to prove this, we used implicit differentiation, and also from this we proved that the derivative with respect to x of ln of x is the same as 1 over x. And this one here, actually, these rules, you have to know them by heart, especially when we will be doing u substitution and integration by parts. Knowing these things is always good, because it's always going to be beneficial. It's always going to be, actually, it's going to make your life easier. Just trying to remember something here. When it comes to integration using u substitution, what is more important is not only knowing these formulas. These formulas, you will need to know them when you're doing antiderivatives. And then when you're doing u substitution, you need to know these functions plus the chain rule. And then when you're actually dealing now with the integration by parts, you need to be good with product rule, and also you need to know these things by heart. So they need to stay in your mind. Keep practicing and see what you can do with these nice functions here. Now, I have compiled some examples here so that you can actually try and use these rules, all the rules that are above here. So let us look into this. Number one, want you to use the first principle to find the derivative of f of x is equal to c, where c is a constant. And then I want you to find the derivative of these functions, or differentiate these functions, or find the first derivative of these functions, or find the slope of the tangent line that is touching f of x at point x. So those are actually some of the things that you actually need to keep in your mind, that they are asking the same thing with those things. So you actually having these functions here, they're nice, and then you also have some other more functions here, and we also added some nice functions here, including this last function here. If you can take a look into this function, you can see that this one, we have an independent variable raised to an independent variable. So we are no longer having f of x is equal to x to the power n, whereby this is a constant. This one, we knew that this was a power function, and we know how to find the derivative of a power function, because you just bring the exponent down and then you subtract a 1. But now we have an independent variable raised to an independent variable, so this function here is not a power function. So it is not a power function. And we also know how to find the derivative of f of x is equal to some constant raised to x. We have an independent variable in the exponent, but down here you have a constant, so this one is an exponential function, and we know how to take the derivative of this, because it's going to be a to the power x times the ln of a. But now if you look into this one is an independent variable raised to an independent variable, so it is also not an exponential function. So I've also added this function as a bonus into how to actually find a derivative of a nice function like this. Can we use the information that we have here? Can we use the information that we have here? I don't know. It is going to be time for you to actually find out when we are actually finalizing by finding the derivative of this weird function here. And also, one thing that I would say before we can actually start solving these exercises, just grab a piece of some snack, because this video is going to be long, because there are so many questions here, as you can see. And then you can sit down and try and solve these questions. You pause the video, find the derivative of this, find the derivative of that, find the derivative of this, find all of them, and then you can watch now and see if your answers are correct or not. Because if you just watch up to the end, you don't know if you know this or you don't. So start by actually practicing, and then you check if your answers are matching with what I have. If they are not, you will get some explanation of what is actually going on. Let's start with number 1 and see where we can actually get to with number 1. Number 1 was actually saying use the first principle to differentiate f of x is equal to some constant c, where c is a constant. So we agreed to that this is just a constant. What is the first principle saying? The first principle is saying if you want to find the first derivative with respect to x of this function, all you need to do, you need to take the limit as h approaches 0 of f of x plus c minus f of x all over some h here. Now, if you look into this particular function here, if you were to draw that function, you will find out that it is going to be a constant function, and here is going to be c if c is positive, or it's going to be below the x-axis if c is negative. But what is important here, if this point here, suppose this point is going to be x, so when I am picking, this one is not supposed to be c, it's supposed to be h. So when I'm picking some h, in other words, I want to add some h so that I get a value that is so close to x, you will find out that the output at that function here, when I'm going there, I'm always gonna hit this value here, which is c. So this is going to be the same as the limit as h approaches 0 of f of x plus h. No matter what I'm going to add here, because this function is constant, this value here, or the value that I will end up hitting in that function, is always going to be a c. So I will have a c minus, I'm going to have a c minus f of x. F of x is just that c, and then you divide this whole thing by h. What is nice about this whole thing is that we're going to have h approaches 0 of c minus c is going to be 0 divided by h. And now, if you look into this here, whenever I am picking h, h is not 0, but it is so close to 0. So that's what is important here. H is not 0, but it is so close to 0 such that whatever that value, when I'm plugging it here, is going to be rounded off to 0. For instance, if I have 0, 1, 2, 3, 4, 5, 6, so I want to place as many zeros as I can actually have here, so that this value that I have, this calculator here is not going to actually realize that I actually have this value. So I can continue and say I'm going to add another zeros here. I'm going to add as many zeros as I can here. I want to make sure that you can actually see here that I have a 1 in the end here. So if I have 1 here in the end, you will find out actually this value here, if I will, let's say I wanted to now to add at the end, I have this answer here, which is this. Now if let's say I wanted to add a 1, you will see the answer is just 1, which means this value here, the calculator is just thinking, this is just insignificant, just 0. So this is rounded off to be a 0, but it's not a 0, which means that I can divide a 0 by a number that is not 0, even though it's close to 0, but it's not 0. So if I take 0 divided by any number, I can always get h approaches 0 of 0 divided by 0 is going to be 0, and of course the limit of a constant is always going to be that constant. The reason I'm explaining here that you can always divide with that is because I know that whenever I have 0 over 0, there is a way to deal with this limit, or there are ways to deal with that limit. Or when I have a number over 0, there is one way to deal with that. So I want to make sure that here I am not getting a 0 over 0. That is why now I can actually just say I am going to just divide by 0. I get a 0 there. So don't get confused. This is just as easy as it is. And now let's start with number 2. Number 2, we had our f of x, wanted to differentiate What was the question here of number 2? Just to make sure here. Differentiate the following functions with respect to the given independent variables by using power rule or product rule or quotient rule or chain rule where it is applicable or appropriate. So that's what we actually wanted to do here. We have f of x is equal to 3x squared plus 1. And now here, they are not saying use the first principle. We only use, most cases, the first principle when it is specified because it's hard to follow all the rules of limits. So only use the first principle when you are forced to. But if you know a rule that you can use, just go for it. Or use the principle, first principle if someone is saying use it. Because if they are saying, you know that the derivative of a constant is always going to be 0. But if you were just going to say that, you were going to get 0 in this question because the question was specific. Use the first principle. So they only want you to use this or to do it this way. You can't just say it's 0 because you will end up getting a 0 instead of 4 marks or 5 or sometimes 3. Just follow this if they are saying use the first principle. Now, the first derivative of this, of course, the first derivative is the same as dx because this variable here is x. So we're taking the derivative with respect to x of 3x squared plus 1. And of course, this one, it is the sum of two functions. So we're going to take the derivative of this one and take the derivative of that, and then we sum them up. Or simply say that I can always pull the constant out and take the derivative with respect to x of x squared and then plus the derivative with respect to x of 1. So if you look into that, what is the derivative of this? This is a power function. So you bring the exponent down and then you subtract a 1 from the exponent. This one, you know, the derivative of a constant is always going to be 0, and 2 times 3 is going to be 6x. So that is actually the derivative of that particular function there. This one was A. Let's go to B. And then B is saying that, what was our B? Our B was, it was h of y. H of y is equal to y squared plus 7y. And if you look into this, the independent variable here is y. So here we want to find h prime of y. So if you look into this, our y here is no longer the subject of the formula because here the independent variable is y. So you don't have to end up saying, hey, I need to actually use implicit differentiation. No. Here y is actually the independent variable. So this is going to be dy because the independent variable is going to be y of y squared plus 7y. Of course, this is going to say, you can say that this is actually a power function. So you bring the 2 down, you multiply by y, and then you subtract a 1. So it's going to be just a y plus 7 times y. So we have a 1 here. When you bring it down, it's going to be 7 times 1, and then you have a y raised to 1 minus 1. So that's actually what you are left with, 2y plus 7. That's the derivative. Let's look at number C here. Number C was, we had f of x is equal to e to the power x times x, or x was in this side, still the same thing, it doesn't matter, times the square root of x. We don't know how to, we know how to take the derivative of x. We know how to take the derivative of e to the power x, but we don't know how to take the derivative of the square root of x. We only know how to take the derivative of power functions. So we need to change this to a power function. So this is the same as x raised to e to the power x all over x times 1 over 2. So x raised to 1 over 2 is the same as that. And now if we wanted to find the derivative with respect to x of this whole thing, we need to remember that we have a numerator and the denominator. And we know this is going to be low d high minus high d low divided by low low. So this is actually one shortest way. So low means the denominator, so we're going to have x times x, the denominator is it is, and then we multiply by the derivative with respect to x of the numerator, which is x times e to the power x, and then minus, we keep the numerator as it is, and then we multiply it by the derivative of the denominator, which is x raised to 1 over 2, and then you divide this whole thing by x raised to 1 over 2, and then you square it up. So that's what you do. This is not hard at all. So once you have that, you can see that we still have x raised to 1 over 2 times, what is the derivative of this? We have two functions here. There is one function multiplied by another function. So when you have a product of two functions, you need to use product rule. So the product rule is saying keep this as it is. So you keep e to the power x, you multiply by the derivative of the first function, which is x, and then you add, you keep the first as it is, you multiply by the derivative of the second, which is e to the power x, and then minus, and then we have x and we have e to the power x, and then what is the derivative of this function? You bring the 1 over 2 down and you keep the x as it is, and then you have 1 over 2, you subtract a 1, and then you divide this whole thing by, of course, you can see that whenever I have a to the power m, and then I take the power of that, this is just the same as a to the power n times m. So I'm just going to multiply these two, so this 2 and that 2 will actually cancel out, and now we have an x there. So this whole thing now will end up going back to what it was. So I still have x to the power 1 over 2, and then inside the brackets here, I'm still going to have e to the power x. Don't leave these brackets out because you'll end up making a mistake, because this whole thing is multiplying everything that was inside. So if you don't have these brackets, you'll end up losing some marks. As you can see here, this multiplied by that is why you needed the brackets. And then what is the derivative of x? We know that the derivative is always going to be 1, because if you're bringing a 1 here, you'll end up having a 1 here, and then 1 minus 1 is going to be 0. X to the power 0 is 1. 1 times 1 is just a 1, and then plus x. What is the derivative of e to the power x? The derivative of e to the power x is still e to the power x. That's what is important here. And then we are left with this now. Just want to simplify a little bit further. So here we have a minus, we have x e to the power x, and then this side here we still have 1 over 2 times x raised to 1 over 2 minus 1 is the same as 1 over 2 minus 2 over 2, because I want to have a common denominator. 1 minus 2 is going to be minus 1, and then the common denominator is 2. So we have that nice thing here, and we're dividing this whole thing by some x. So basically here, if you can notice something, I am going to let me first simplify this and make sure that it actually looks nicer. If you look into this part here, this part is just x raised to 1 over 2, and then inside I have e to the power x, so I have e to the power x, and then I take this e to the power x, I take this e to the power x. Inside here I will end up having, if I take this one is taken out, and then I'll be left with 1, plus if this one is taken, I'll be left with x there, minus, if you look in here, you will find out actually we just have x times e to the power x, and then inside here I have a 2 in the denominator there, and then having a negative here is just saying that we are actually having x in the denominator 1 over 2, but now it's positive because I've just placed it in the denominator. I still have this x here. I don't want you to forget that x. Keep it as it is, and then if you look into this part here, I have x and x raised to 1 over 2. So what is important here is that there are two things that you can actually do here. I have this x which is raised to 1. I have this 1 over minus a 2. If you want to, you can go to this step, or you can just move from here having an x raised to that. So whenever I have a to the power n times a to the power m, this is the same as a to the power n plus m. So multiplying powers of the same base, you just add exponents. So this one here and that one, we still have an x. So I have a 1 there. I can just say 1 plus minus 1 over 2, or just minus 1 over 2, because if you have plus and a minus, you always take a minus. You have plus minus, so we're just gonna take a minus there. So we have this, and you know that 1 minus 1 over 2 is the same as 2 over 2, because I have a 2 here. I want to have a common denominator, so this is going to be x raised to, I have 1 minus 2 is going to be 1, and then I take 2 as a common denominator. Or you can realize here, because this one is in the denominator, so you subtract here, and then you'll end up having that whole thing there. So either way, you can either move from here to there, or can move from this step to, when it comes to this part, to what I'm going to write now, which is going to be x raised to 1 over 2 e to the power x, and I still have 1 plus x here. And then when it comes to this part here, I'm going to just say I have x raised to 1 minus 1 over 2 times e to the power x all over a 2. This whole thing, I'm going to divide it by x. And then I can proceed here and say that I still have x raised to 1 over 2, e raised to x, and then I have 1 plus x minus, and then I'm going to use that and say I know that this is the same as x raised to 1 over 2 times e raised to x all over a 2. And then I can say that this whole thing, I'm going to divide it by an x. And then if I proceed here, I can see that I have x raised to 1 over 2, e raised to x, x raised to 1 over 2, e raised to x. So this whole thing is going to be x times 1 over 2, e raised to x. And then inside here, if this one is taken, this is what will be left. I have 1 plus x. If this one is taken, this is what is going to be left inside. So I end up having 1 over 2. This is taken, so we'll be left with 1 over this 2. And then this whole thing divided by x. And you can see now that it's looking a little bit nicer, that I have this x here, which is raised to 1. So this whole thing, because I have an x and an x, so I end up having x raised to 1 over 2 minus 1, which is this one. When dividing powers of the same base, a raised to n divided by a raised to m is the same as a raised to, we start with this n in the numerator, and then we subtract the 1 in the denominator. I hope you still remember this. So that's what we are doing here. This x and this x, I can see that I have this one here and that one here. And take note that whenever I have this box here divided by, I'm going to say I have this box times some another box here divided by this box star here, right? This thing here is the same as just saying the box divided by this box star here times I have this here. And this thing is just the same as having this box times this whole this diamond here divided by this box star. So you can either choose this or that when you have that. This is the same thing that we are doing here. Instead of dividing this whole thing, I just decided this x is only dividing that part. Hence, I'm saying I have bases that are the same, so I have to separate the exponent. And everything here, I left it as it is. So I have 1 plus x minus 1 over a 2. So if you look into this here, I know that 1 because here I want to have a common denominator so that I can separate, or you can just punch it in a calculator, this thing. 1 is the same as 2 over 2. Where is this 2 coming from? Is the one that is in the denominator. And then you can see that I have x raised to 1 minus 2 is going to be minus 1 over 2. 2 is a common denominator. And I'm left with the x e into if I have 1 minus half is the same. I mean, I had 1 minus half here, so I know that this is still going to be x minus no. This one, it was 1 minus no, this one was 1 over 2 minus 1, right? That is why we ended up having a negative. But in this case now, we'll end up having 1 minus 1 over 2, and 1 is the same as 2 over 2. 2 minus 1 is going to be plus 1, and then we take the common denominator as 2. So you can either stop here, or you can actually fix this and say that this is just the same as e to the power x, and then times x plus 1 over 2 all over x raised to 1 over 2, and then you can simplify further and say you have x, and then here you end up having x plus 1 over 2, and then in the denominator you're actually having the square root of x. And if you like it, you can still proceed and say actually this is e to the power x, and you wanted the common denominator here, and you can say that you know that x is the same as 2x divided by 2, and then plus 1 over 2, and then you divide this by square root x. And of course, I'm going to take the common denominator here and say I actually have 2x plus 1 divided by 2, and then this whole thing divided by square root x, and this final thing is going to be e to the power x times 2x plus 1, and then this whole thing divided by 2 times square root x. So you can always either end up or just end up there, it's still fine. But because the equation had the square root in it, then you're supposed to end with the square root. So you can either end here or there. If they really need the square root, you can end here. But now here we're just simplifying using some nice algebra. I hope you can still get this whole thing, that even though it looked so complicated, the final answer is just so easy like that. Now let us proceed and look to some of the easiest things they are here. What was this? This was C. Now we are at D. So we have a D here. D is saying find the derivative of f of x where f of x is equal to 3 minus x all over x cube minus 3. Of course, you have a numerator and a denominator here, and you know that f prime of x is always going to be if let's say you have f of x, if let's say you can see that we have f prime of x, and this one is equal to some h of x divided by g of x. This one is just saying that take whole d high, this is g, whole d high, so you keep g as it is, you take the derivative of the numerator, and then you subtract, you keep the numerator as it is, and then you take the derivative of the denominator, and then you keep the denominator, and then you square it up. So the denominator here was x cubed minus 3, and then you wanted the derivative with respect to x of 3 minus x, which is the numerator. Subtract, you keep the numerator as it is, and then you take the derivative with respect to x of the denominator, which is x cubed minus 3. You divide this whole thing by the denominator, which is x cubed minus 3, and then you square it up. Of course, this one we don't usually simplify it by expanding, we keep it as it is, so that if it happens that there is something common in the numerator, we can cancel it out. Or if there are factors that are also factors of this, we can cancel it out and factorize this. But in most cases, we keep this with this square until we are close to the end. So here we're gonna have x cubed minus 3, and then the derivative of this is going to be the derivative of this minus the derivative of this. The derivative of 3, we know that is going to be 0 minus the derivative of x. We know that it is just a 1. So we're done with that part, and we have 3 minus x. And then now we want to find the derivative of this. The derivative of this minus the derivative of this difference here. So we're going to take the derivative of x to the power 3, which means it's going to be, because this is a power function, it's going to be 3 times x, and then we subtract a 1 in the numerator. So we end up having a 2 there, minus, what is the derivative of a constant? It's always going to be a 0. I want you to know this. The limit of a constant is that constant, but the derivative of a constant is 0. So don't make mistake when you're dealing with limits and say, no, the limit of a constant is 0. No, the derivative of a constant is a 0, but the limit is that constant. And of course, we're going to keep the denominator as it is. We square it up. And then, of course, 0 minus 1 is going to be minus. So that whole thing is going to be minus times x cubed minus a 3. And then minus here, I will end up having a 3 minus x, and then what is inside here is going to be that 3x squared. 0 is still insignificant, it's not that important. And if you take a look into this, we can always divide the denominator by x cubed minus 3, and then we square it up. And if you take note into this, you will find out actually that this whole thing is going to be minus x cubed, or instead of just keep writing this, I'm going to expand. Minus times x cubed is going to be minus x cubed. Minus times minus is going to be plus 3. Minus times a positive is going to be positive 3. Minus times a minus, we are actually starting to have an issue here. So we can't just do that because we still have to multiply with that. So instead, I'm going to take this to the other side before I can expand so that I don't end up confusing you. Let me leave it like this. So I'm just switching these two, but the minus is still there. And then I still have x cubed minus 3, and then I have square there. And then I still want to expand this. The reason I stopped is because I don't want to end up expanding only this part, but I still have a multiplication here. So I need to first multiply this, and then I will take the sign later. So I'll end up having minus x cubed plus a 3, and then here I have a minus. So 3x squared times 3 is going to be 9x squared, and then 3x squared minus x is going to be minus 3x cubed. So at least now I know that this is 9x squared, and then here I have x cubed, and then I divide this whole thing by x cubed minus 3, and then I square it up. And then I can proceed here and say I have minus x cubed plus a 3. Minus times a positive is going to be minus 9x squared. Minus times a minus is going to be a plus 3x cubed. And then I divide this whole thing by x cubed minus 3, and then I have a square there. And then if you look into this here, I have minus x squared. These two are like terms, so I can add them. So I have 3x cubed minus x cubed. I will end up having a 2x cubed, and then this one here is still going to be there. I have 9x squared, and then I still have this 3 here as it is, plus a 3, and then I can divide this whole thing by x cubed minus 3, and then I have square there. And you can try and say I'm going to actually simplify this, factorize this so that I can cancel it, but for me I would say that you can stop there. It's still fine. And if you want to know whether you should move forward or not, one thing that I would say here, I would say look at the factors of 3. if you look at the factors of 3 here, if you are plugging in any factor of 3, the one that is actually giving you a 0 in the numerator and also a 0 in the denominator, that one is going to tell you if you should factorize here or not. If there is such a factor that is making this 0 and this 0, then you can continue to factorize this and factorize that and cancel. But for me, I'm just going to end it there. Don't want to waste your time. And then the next one was we wanted to, what was this? This was number D. So we want now to talk about number E. Number E is saying we had f of t, which was actually equal to 1 over t plus a 1. Of course, this is just the same as t plus 1 raised to minus 1. So whenever you have a minus, this goes to the denominator. So this is the same as that. So you can either use quotient rule here or use the chain rule. For me, I'm just going to use chain rule because it's going to make my life easier. Right, so that's what I actually want to. What I'm actually doing here is not something new, because you can even see here someone might have decided that I have an x here, I have an x there, I have an x and I have an x, and then someone might decide that actually this is just gonna be the same as x raised to, because I have a 1 there, I can just say I have a 1 minus 1 over 2 e to the power x, and they say actually this is going to be 1 is the same as 2 over 2, so we'll end up having x raised to 1 over 2 e to the power x. And instead of using the quotient rule here, they end up using the product rule, because I have this function here, I also have that function here. So you can play around these two things, but you're still gonna get the same answer. It's the same thing that I'm actually trying to do here, that this you can use the quotient rule here, or you can use the chain rule. I'm gonna go with the chain rule because for this particular question is easier. Just unfortunate for the previous problem that we ended up using the quotient rule when there was a product rule which was easier. But either way, hope you have learned something there. Let's focus on this here. One thing that I know for a fact here is that if I had a function h of x equal to, you can see that I have some function here and I had some x raised to minus 1. I know that this one is actually a power function. So to find the derivative of this power function, all I need to do, I need to bring the negative 1 down. I have an x and then I have a minus 1 and then I subtract another one there. So you just subtract 1 in the exponent, you bring that exponent, the original exponent there, and then subtract a 1. That was going to be a derivative, was going to be minus 1 over x squared. I know how to take the derivative of this, but I don't know how to take, if I have a function here, I know how to take the derivative of this. So what you actually do here, you wanted to change this function to a function you are actually familiar with. That's what the chain rule is actually saying. So since you know how to take the derivative here, if there was an x here, x raised to minus 1, you know how to take the derivative of this. So what you do here, you just say let u to be what is sitting in the value of x here. So I'm going to take this as u, so it's going to be t plus 1. And after that, I want my y. My y is going to be, I'm going to replace this whole thing here. So my y is going to be u raised to minus 1. And now I know how to take the derivative of this. So I will know how to take the derivative of this, and I know how to take the derivative of that. So f prime of t is actually going to be dy with respect to t, because replacing a y here, I'm still replacing a u here. But this u is still that, so when I'm taking the derivative of this with respect to t, I should get the same thing. But if you look into this function here is not written in terms of t, it is in terms of u. So if I want to take a nice derivative of this, I want to just take the derivative of y with respect to u, and then this u need to go away because it was not part of this, so I'm going to have du dt. So what is the derivative of this? This is going to be easy. I want d du of u to the power minus 1 times d dt. My u is t plus a 1. What is the derivative of this? I know it because I have to bring a 1 down, this minus 1 down. I keep the u as it is, and then in the exponent I subtract a 1, and then times. What is the derivative of the sum of this? I know that the derivative of this is always going to be just the derivative of just t with respect to t is going to be 1, plus the derivative of a constant is going to be a 0 there. Because here I know that when I'm taking a derivative, there is a 1, I'm going to bring a 1 down. I have a t, there was that 1, so I will have a 1 minus 1. Of course, if you look into this, I will end up having this is the 1 and t to the power 0. T to the power 0 is still a 1. 1 times 1 is just a 1. That's where this one comes from. And then this whole thing is going to be minus 1 times u raised to minus a 2, and then this one is still going to be just 1 plus 0 is 1. So here I will end up having a minus 1 divided, because we have a negative there, I have a u squared. Because this function that was given to me did not have a u, it has a t, I replace that u back. So this is going to be minus 1 over t plus 1 squared. So that is actually the derivative we're looking for, or f prime of t. Let's go to another function here, which was f. We had f of x, it was equal to the square root of x to the power 5 plus 1. Again, if you look here, I don't know how to take the square root of something. I know how to take, if my h of x was equal to the square root of x, which is the same as x raised to 1 over 2. I know how to take the derivative of this. And the derivative of this whole thing is going to be, h prime of x is going to be 1 over 2 times x raised to 1 over 2 minus 1. And 1 is the same as 2 over 2. So this is going to be end up being 1 over 2 times x. 1 minus 1 is 1 minus 2, because this is 2. 1 minus 2 is going to be minus 1 over 2, because 2 is a common denominator there. And then this whole thing will end up being just 1 over 2 square root x. I know this would end up being that. But now I have square root of something. So what I do, I let, because I'm supposed to just have an x square root of x to just find the derivative. So what is sitting there, I just let my u to be what is sitting there. So it's going to be x to the power 5 plus 1. And I'm going to let my y to be, I'm going to replace that whole thing, which is that, by u. So my y is going to be square root of u, which is just the same as u raised to 1 over 2. And then after that, my f prime of x is still going to be actually dy dx, because the independent variable is x, so I have to take this with respect to x. But if you look here, my y is not in terms of x, so I have to take the derivative of y with respect to the variable that is there, so it's going to be du. But du was not part of this, that is why I have to find out du dx, which is that. So these two can actually end up cancelling or undoing each other. So if you look into this here, yeah, someone might say it's not really undoing, this is a chain. I'm just trying here to give you a mindset of actually remembering this. It's not saying that this is going to cancel with that. We're not cancelling out anything here. I just wanted to give a student the mindset of not forgetting this whole thing, so that they can always remember that, oh, dy du divided by that. And the more you do examples, you don't even need to write this whole thing. You can just keep this as it is, take the derivative, and then you end up playing around, and then you will get the answer. The more you keep playing around with these examples, you will be fine. So I have d du, but what was my y? My y was or u raised to 1 over 2, and then times d dx, but my u was x to the power 5 plus 1. And if you look carefully into this, you know that if you want to find the derivative of something raised to 1 over 2, as long as you have this is going to be 1 divided by 2 root x. No, because this is u, 2 root u. Same thing here, like this, of the same. But if you wanted to go through the process, who am I to stop you from doing that? This is just going to be 1 over 2 times u raised to 1 over 2 minus 1, and then times, and then this whole thing here is going to be, the derivative of this here is going to be 5 times x raised to 5 minus 1, and then plus the derivative of a constant is 0. And then if you look carefully into this, this one is going to be 1 over 2 times u raised to minus 1 over 2, and then this thing inside here is going to be 5 times x. 5 minus 1 is going to be a 4, and then you can proceed here and say this is minus, so it needs to go to the denominator, so you end up having 1 divided by 2 root 2u raised to 1 over 2. Because we are positive, it's going to be negative in the denominator, and then at the same time u raised to 1 over 2 is still the same as root u, and then you multiply this whole thing by 5x to the power 4, and if you carefully evaluate this is just going to be 5x to the power 4 divided by 2 root u. But we did not have u in this equation here, so I need to replace u back, which is 5 to the power x to the power 5 plus 1. So this is going to be 5x to the power 4 all over 2 root x to the power 5 plus 1. That's what we're actually looking for in this particular question. Let us look now at G. What was our G? Let me look at G. So our G is saying we have f of x is equal to, I have 3x here, and then plus a 5 all raised to 3 over 2. Of course, if let's say my function was h of x, it was equal to x raised to 3 over 2, I would be able to find it, but now I have something that is sitting in the value of this x here. So what do I need to do here? What I actually need to do now, I just need to let u to be what is sitting in the value of x, which is that. So we end up having 3x plus 5, and my y is going to be, I'm going to just replace that whole thing by u. So my y is going to be u raised to 3 over 2. And now, of course, if I want f prime of x, I know that this is supposed to be dy with respect to x, what was inside, dx, but my y is in terms of u, so I'm going to have dy du times du dx. Of course, I have du first. My y was actually u raised to 3 over 2, and then times ddx, and my u was 3x plus a 5. If you look carefully into this, all I need to do here, I just need to bring 3 down, and then I multiply by u, and then I subtract in the exponent 1, and then I multiply this whole thing here by, what is the derivative of 3? X is going to be 3 plus the derivative of a constant is just a 0. You can see that 3x is going to be something of that nature. And now if you look into this, of course, if you're still wondering what is going on here, you know that to find ddx of 3x, this is you pull 3 out, and then you find ddx of just x. So dx is just a 1. That is why you end up having a 3 dx. Okay. Now that you have this whole thing here, all you need to do is simplify. Having a 1 here, I have a 2 there. All I just need to do here, I just need to change a 1 to 2 over 2. 3 minus 2, let me keep this 3 over 2 here. 3 over 2 times u. 3 minus 2 is going to be 1 over 2, and then times a 3 there. 3 times 3, I know that's just a 9, times u raised to 1 over 2 all over a 2. I am not going to change this to a square root because it was given in this form here. There was no square root. And then my u is 3x plus 5, so this whole thing is going to be 9 times 3x plus 5 all raised to 1 over 2 all over a 2. So I'm gonna leave it like that. I'm not gonna do anything from this. So that's how we end up dealing with this. Let's go to h. Our h is actually saying that we have f of t is equal to e raised to t squared plus 3t. And of course, if my function h of t was actually e raised to t, I know how to find the derivative of that because h prime of t would be just the same thing, right? So now instead of having just a t there, I have something else. So I am going to let what is sitting in the value of t to be u. So I will end up having u is equal to t squared plus 3t, and my y is still going to be the same function except that that whole thing will be replaced by a u. So I will end up having e raised to u. And then after that, my f prime of t, which is just supposed to be dy dt because the independent variable is t there. I notice that my y is not in terms of t, so I want it in terms of u. So I'm going to have dy du times du dt, which was this dt here. And then after that, I know actually what was my y. So this is going to be du of my y was e to the power u times dt. What was my u? My u was actually t squared plus 3t. What is the derivative of e to the power u with respect to u? Is still going to be the same thing, and then multiply by the derivative of this. Take note that I always have big brackets when I have to deal with this because I don't want it to end up making mistakes. Always have those two brackets. And then this one is a power function, so I know that I have to bring the 2 down, have a t, subtract a 1 in the exponent, so I still have a 1 there, and then plus. What is the derivative of this? We know that this is going to be just a 3. Of course, still similar to some of the things we did above. And then the next thing that I just have to do, I have to replace this u by t squared plus 3t. That's all there is. So this is e raised to t squared plus 3t, and then multiplied by 2t plus 3. That's all you need to do in h. Let's move forward and go to other problems here. The next problem is we have hi. So we have f of x. Our f of x is the same as e raised to x times sine of x. So we have x times sine of x. So of course we're going to follow the same thing here. I know that if my function was h of t is equal to e to the power x, I will actually be having the derivative of this with respect to x to be e to the power x, still the same thing. But now, instead of having an x, I have something that is sitting there. So I let that something that is sitting in the value of x to be u. So I have my u equal to sine of x, and then my y is going to be, I'm going to replace that whole thing by a u. So I will end up having e raised to u. And then f prime of x is supposed to be the same as dy dx because the independent variable here is x, so I'm gonna end up having that. But my y is not in terms of x, it is in terms of u. So I wanted to have my dy with respect to u times du, which this one was nowhere to be found, so I wanted to end up having something of that nature but in the numerator. So my du, my u was in terms of x, so I end up having my dx there. What is my y? So I have du, my y is e to the power u, and then times dx. My u is actually x sine of x. Of course, if you take a look into this, when you have e to the power u and u, so I'm differentiating with respect to u, the derivative of e to the power u is still the same thing. So we'll end up having e to the power u times. I'm going to have big brackets here. Why? Because I don't know here if I'll end up having addition of so many things. I don't want to end up making a mistake. But if you notice something here, I have a product here, x times sine x. Sine x is a function, x is a function, so I have to use the product rule. So if I wanted to use the product rule here, all you need to do here, you keep the second as it is, and then you multiply by the derivative of the first, and then you keep the first as it is and you multiply by the derivative of the second. So that is what is actually happening here. So I have this. Even if it's there, you can see that is dx dx. This is the same as dx dx, which is just 1. So I end up having e to the power u inside. The derivative of x with respect to x is just going to be 1 because I had x to the power 1. This was x to the power 1. So I will have to bring a 1 down and then separate a 1 there, and end up having 1 times x to the power 0. X to the power 0 is just a 1. 1 times 1 is going to be a 1. So that is why this is a 1. Or just dx divided by dx is just 1. So here you'll end up having sine of x plus, I still gonna have an x here. What is the derivative of sine? The derivative of sine is just going to be cosine of x. And we'll replace this u here by whatever u was, which was x times sine of x. So this is going to be u e raised to x times sine of x, and then inside here I will end up having a sine of x plus x times cosine of x. That's what we're actually looking for here. It's not that deep. And then the next one was actually a j. J was saying we had our g of x, and our g of x was e raised to cosecant x. And then if you look into this, this was actually, we had some brackets here. It doesn't matter if you use these square brackets or these ones. Sometimes others prefer use square because these ones are not talking about intervals. So you can just use this there just for multiplication. Square brackets to make it cleaner, or use these ones, depend on which ones that you actually see they're actually making things clean for you. And then outside we actually end up having a tan of x. So if you look into this, whenever I have a to the power, a power of a power is always going to be, you keep this one as it is, and then you just multiply these two. So the same thing that I'm going to do here, I'm going to multiply these two. So I end up having e raised to cosecant x times tan of x, right? So this is just written like this so that we can find its derivative. What is important here, I don't want to make this thing so hard than it is here. If let's say we had e to the power x, we had let's say we had a function here, and our function was h of x, it was equal to e to the power x. We know that we would say our derivative is e to the power x, is still the same thing. But now I have e to the power something, so I don't have an x. So what I do, I let u to be what is sitting in the value of x, that whole thing. So it's going to be cosec x times tan of x. You getting it? And then after I have this whole thing here, I know that my y now is going to be, I'm going to replace this whole thing by y, so it's going to be e to the power u. I'm going to replace this whole thing by u so that you can get that. And then the derivative with respect, what were we getting here? It was g. The derivative with respect to x of g is going to be the derivative now of y with respect to x, because the independent variable here is x. So this is going to be the same as dy, because here my y is in terms of u, so it's going to be dy du times du dx, which was this one, dx. Another thing that I wanted to mention here is that whenever you have dy dx, you must know that this is just the same thing as ddx of y. So I don't want you to end up getting worried of where is this brackets coming. No, this one thing is also saying the same thing, still the same thing. So that if you are actually having dx of x, you know that this is still the same as dx, which is just 1. So this whole thing is going to be du, but in the value of y, I know what my y was e to the power u, and then times dx, but in the value of u, my u was actually cosecant x times tan of x. If you look carefully into this, I have a u here, I have a u there, then the derivative of e to the power u is still going to be e to the power u. I'm not going to change anything. And now here, I want you to notice something, that I have a function here, I have another function there, so I have a product of two functions, so I'm going to use product rule because it's a multiplication of two functions. So you keep the second as it is, you take the derivative of the first, which is cosecant of x, and then you add, you keep the first as it is, cosecant of x, and then you multiply by the derivative of the second, tan of x. So of course you close your brackets. Right, now that you have closed your brackets here, what are you going to get? You still have e to the power u, and then what is inside? I still have tan of x, and then what is the derivative of cosecant of x? Remember that when we were finding the derivative of cosecant x, we said that it is the same as the derivative of cosecant x. It was minus cot of x, because and then times cosecant of cosec x. I want you to actually still remember that cosecant derivative of it is always going to be cot and cosecant. And then after that, we still have cosec of x, and then what is the derivative of tan? And we know that the derivative of tan of x is just going to be sec squared of x. That's what is important about this whole thing. Can we simplify now? This one here, I still have e to the power u, and then inside here I have tan. I'm gonna keep the tan as it is. I have a minus here, so tan times minus is going to have a minus here. I have tan of x, and then I still have a cot of x, and then I still have cosec of x, and then here I still have plus, and then I have cosec of x, and then times sec squared of x. Right, now if you notice, what is cot of x? Cot of x is still the same as, cot is the same as 1 over tan of x, right? And then if you look here at cosec of x, you know that cosec of x, let me leave this as it is for now. I will deal with it at a later stage. Here we're still gonna end up having e to the power u, and then I have a minus as it is, and then tan and tan will cancel out, and now I have minus because this and that will cancel out, and now we'll end up having cosec of x, and then I will end up having a plus, right? And then here I still have a cosec of x, and then I have times, and then I have sec squared of x. Now what is important here is that we can continue to simplify and factor maybe cosec out cosec out, and then I end up having 1 minus this thing. So what I'm going to do here, I'm going to factor out this one here. So I'm still going to have e to the power u, and then I have cosec of x, and then inside I have minus 1, and then here this one is gone. I will have plus, I have sec squared x. Now if you look carefully into this, you will end up realizing actually that inside here I have minus 1, and sec is the same as 1 over a cos of x. So this whole thing now, it is squared, right? So squared, this is actually squared. Or because this whole thing is actually squared, you know that 1 squared is still going to be actually 1, and then in the denominator you will end up having something nice as cos squared x. Hope you can still see the difference here. Okay, and then if you take this as it is, you will end up having cosec of x, and then here there is nothing in the denominator. Here is a 1, but I want to have a common denominator. So if I look carefully into this, there are 2 ways to do it. Okay, several ways. What I can say here is that if I have, this was minus 1, 1 is the same as 1 over 1. So I can say that 1 is still the same as cos squared x divided by cos squared x. So this one is cos squared. I don't know what I wrote here. So I have cos squared x. So I take this as it is, up and down. So this divided by that, I know that is going to be a 1 because I want to have a common denominator. So what is a common denominator here? Is going to be cos squared x, and then in the numerator here, this divided by that is 1 times that. I'm still going to have minus cosine squared x, and then plus, and then this one divided by that is still going to be this is going to be 1, and then 1 times 1 is still going to be a 1. And one thing that we all know is that if I have sine squared x plus cosine squared x, this is always going to be 1. Or if I have sine squared x, I know that this is always going to be, I take this to the other side, it's going to be 1 minus cosine squared x, or minus cosine squared x plus 1. So this whole thing here is just the same as sine squared x. So this is going to be e to the power u of cosecant x times. So this one here is just the same as sine squared x divided by cosine squared x. And you know that tan of x is the same as sine of x divided by cosine of x, which means that if I'm actually squaring this whole thing here, I'm actually squaring this whole thing here. But if I'm squaring these two things, it is the same as just squaring sine and squaring cos in the denominator. So this is just sine squared. So if you look carefully into this part here, we are actually having e raised to u times cosec of x. This whole thing is just going to be tan squared of x. So you can still proceed here because this is 1 over sine, and cancel 1 of the sine, and then you are left. But I would say stop here. Stopping here is still fine, but if you want to proceed, this one is 1 over sine of x, and this one we know that it is sine squared, or sine of x times sine of x divided by cosine squared of x. This and that cancels out, and now you are left with this divided by that times that, e to the power u, and then you have sine of x divided by cosine of x. It's still going to actually not we have a square here. We're still gonna end up getting something here which is e to the power u, and then this is going to be sine of x divided by cos. We know that is going to be tan, so it's going to be tan of x, and then we end up having 1 over our cos is just the 1 over cos is the same as sec of x. So you're still gonna get something of this type. So if you get this answer or that answer or that answer, is still one and the same thing, but it's just that you rearranged certain things. That's why I'm saying you can stop here, but if you proceed, you will end up getting something of this nature. And this is going to be sine, this was actually cos of x, and then you also have cos of x. Cos squared is cos and cos. So 1 over cos, we know that is going to be sec, and then sine x divided by that, we know that it is tan. So you're still gonna get something of this nature, or you're gonna get something of this nature, or you get something of this nature. All these answers are still correct. I don't want you to make a fuss around these things, so just know that all of them are actually correct. For now, let me clean this because I don't really need it. All I need now is just I want to replace what was my u. So here my final answer is going to be E, and my u was actually cosecant x times tan of x, and then down here I still have cosec x tan squared x. So that's what we actually ended up with. That was the final answer because my u was that. Let me just, my u was this. So that's how we ended up dealing with this nice function here. Now I want us to take one last question in number 2, and then we go to 3, and then we go to 4, and then we can call it a day. We had f of x, which was equal to the square root of tan of x, and you know that if our function was just square root of x, which is the same as x raised to 1 over 2, its derivative was going to be easy because we're going to bring 1 over 2 down, and then we do the thing, and we'll end up having 1 over 2 times square root of x. We have done a problem of that nature before, so we know that we'll be getting that. But instead of having an x here, I have a tan. So I am going to let u to be what is sitting in the value of x to be tan of x. And now my y is going to be the same function, but now I'm going to replace that thing that is inside by u. So I'll have a u which is the same as u raised to 1 over 2. And then now our f prime of x is actually going to be dy dx, because the independent variable is x, but my y is not in terms of x, so I want to have dy with respect to the variable that I have u, but u was not part of that, so I still have to take u now with respect to the inside variable, which is x. And then if you proceed here, you will find out we will end up having du, but in the value of y, what was our y? Our y was actually u to the power 1 over 2, and then we still have du dx, but in the value of u, I know that we actually ended up having tan of x. And what is the derivative of this? We use this, but instead of having a u here, x here, I have a u. So here I will end up having 1 over 2 square root u, something of that nature, because it's just a change of variable. I have u, but here I have an x, times whatever I'm going to get here. I usually put brackets just in case there is addition of things or subtraction of things, so that I don't end up making a mistake. What is the derivative of tan of x with respect to x? We said that the derivative of tan of x with respect to x was sec squared of x. That's what we said. So we don't really need big brackets like that. This is what we're actually having. So this whole thing, 1 times sec squared is going to be sec squared of x divided by 2 root u, and this is just the same as sec squared of x, and then in the denominator I have 2 root. What was my u? My u was actually tan of x, so I end up having tan of x inside. That's the derivative that we're actually looking for here. Now we are going to number 3. One good thing about this is if you have been following up to this far, I would say take a break, take a break, even if it's just for 5 minutes or 10 minutes. Get some snacks or make some coffee or whatever, just to relax your mind. And then after 5 minutes or 10 minutes, you can come back and proceed, so that you can actually comprehend with what is actually happening here. Number 3a was saying we wanted to find dy dx of x squared plus y squared is equal to 25, and the question was saying use implicit differentiation. So that was basically the question. So basically what implicit differentiation is saying, we wanted to find dy dx without making y the subject of the formula. That's the implicit differentiation. Find dy dx without making y the subject of the formula. So what we can actually do here, we take the derivative with respect to x on both sides. So that's what we are actually doing here. So we get dy dx of 25. What is important here, if this function is equal to that, if this is equal to that, then the derivative of this should be equal to that at every particular point. So if you look into this here, you will find out actually that to take the derivative of this with respect to x, all you need to do, you just need to bring the 2 down, have an x, and then you actually end up taking subtracting a 1 in the exponent, plus the derivative with respect to x of y squared, and then equal to, what is the derivative of a constant? I don't care how much that constant is, the derivative of a constant is always going to be a 0. And then we can see that actually dx of y squared is actually going to be equal to minus 2x. So that is what is important there. And then how can we find the derivative of this here? What is important here is that our y is equal to some function f of x. So we cannot say that y is a constant because there's no x there. This is not the same as saying this was just some, let's say, some constant c squared. If let's say now you want to find the derivative of e squared, you know that e is a constant. So the derivative of this, because e to the power 2 is still a constant, so it will be 0. But in this particular case, our y here is a function in terms of x. So we cannot just say the derivative is going to be 0 there. So what we are actually seeing here, we are actually seeing that we have some function. I'm going to call this function here, this was our y, or this y here is equal to some h of x. So if you look into this h of x here now, we end up having something squared here, because we have y squared, so we have this. If we had x squared, we know how to take the derivative of that. So how will you take the derivative of that? We do the same thing that we did here. You bring the exponent down and then you subtract a 1, and we are good to go. But in this particular case here, we don't have that. So what is sitting inside there is the one that we just say, let u to be what is sitting inside there, right? So it's going to be that. And then now my new I'm not gonna use y because y is part of this. My w is going to be, I'm going to replace whatever is sitting in the value of x by u. So I will end up having a u and then squared. So this whole thing here, if now I am looking for my dy dx, I will have to take the derivative of w with respect to u, and then take the derivative of u with respect to x. That is actually what is happening. So if I'm looking into this particular case here, if let's say this one, I'm going to let it to be my h of x. So this part here is going to be dw with respect to be with respect to, so if you look into this whole thing here, this is going to be actually our y, because this is the function that we have. So we're gonna end up having this with respect to our u, and then we'll multiply this with the derivative of u with respect to x, and then this whole thing here is going to be equal to minus 2x. What is our w here? Our w is u squared, so we'll end up having du of u squared times dx, and then I have my u. What was our u? Our u was actually the y, and then we have a minus 2x there. So basically what is happening now, I have a u and a u, so I can always bring the 2 down, and then I multiply by u, and then I subtract a 1, so I'll end up having a 2 minus 1 times, and then this one is just the same as dy dx. That's it, because I have a y and dx, so it's dy dx, and then I have a minus 2x, and then if you look into this, this is going to be 2u times dy dx, which is equal to minus 2x. And if you proceed here, you'll find out actually that my dy dx here, I can divide on both sides by 2u, so I'll end up having minus 2x divided by 2u, which is the same as 2 and 2 will cancel out, minus x divided by u, which is the same as minus x divided by, what was my u? My u here was actually our f of x, which was the inside function, and this inside function was actually our y, because you can see I have this is actually the beginning of this whole thing. My y is the same as f of x in this particular case. So here I would end up saying, oh, this one was my f of x, but my f of x was actually a y in this case. Therefore dy dx in this particular case is minus x over y. That is what we actually wanted to find out. So that was the derivative that we were looking for here. Let's go and do another problem. Another problem was our b, and we had x times y plus sine of y was equal to x squared, and we still wanted to differentiate implicitly, so we take the derivative on both sides of xy plus sine of y, and then on the right hand side we also take the derivative with respect to x, and then we have an x squared there. And then because we have addition there, we're gonna take the derivative of xy, and then we add the derivative with respect to x of sine of y, and then of course here we will end up having, this one can be simplified to just 2x. And another thing that I want you to realize here is that y here is actually a function, so our y is just equal to some f of x. That's what I want you to realize here. So we have our dx of x times y, which is just this f of x. We'll fix it later. I just want you to get the concept here of what is going on. And then here we have sine of f of x instead of y, and this side we have 2x. Now, how can we take the derivative of this? We have a product rule here. We have a product rule here. We have a product rule here. So we are going to end up saying that, okay, this part here is going to be, we keep the second, so we're going to end up having x, and that because this is a product, this is a function, this is another function, and then we take the derivative with respect to x of the first, which is x, and then plus we keep the first, and then we take the derivative with respect to x of the second, which is f of x, and then plus. And then if you look into this one here, I'm going to leave it as it is. I will tell you why in a moment. So we will end up having sine of f of x here is equal to 2x. The reason I'm leaving this as it is here is because I can see that here we have a chain rule, so we have a function inside another function. So let's take these things one step at a time. Here we still have f of x here, So I'm going to end up having this f of x, and then what is the derivative of x with respect to x? This is just the same as going to be dx dx, or just a 1, or the derivative of this, because there is a 1, I can bring a 1 down, times x, and then I subtract a 1. X to the power 0 is going to be 1, so the derivative of this is going to be a 1 plus. And then we come to this part here. I have x times d dx of f of x, and then plus, this is a plus, I have d dx of sine of f of x, and then is equal to 2x. And then my f of x, I know that it is y, so I have y plus x times d dx, because f of x, this is y, so this is going to be dy dx plus d dx of sine of, for now I am going to leave this as it is equal to 2x, because I haven't done anything with this part. Now I am done here. The only part that is left is this one. I know how to take the derivative. I know how to take the derivative of some function h of x is equal to sine of x, because in this case h prime of x is going to be the same as just cosine of x. But instead of having an x here, I have a function f of x that is sitting inside. So what I'm going to do here, I wanted to let this to be equal to a u. So basically my d dx of sine of f of x, what I'm going to do, I'm going to say let u equal to f of x. It is that function that is sitting inside, and then my w is going to be, I'm going to replace that by u, so it's going to be a sine of u. So this derivative of this part here is going to be the same as du first of w times du with respect to x, which was this x here. I'm using a chain rule here. So if you look carefully into this here, I have du, but instead of w, my w is the same as sine of u, right? And then times dx, and my u here, my u is just f of x. So what is this thing saying? What is the derivative of sine of u with respect to u? You know that if this and that is the same, this is just supposed to be cosine of u times dx of f of x here. I still have my f of x. And if I notice here, my u was actually the same as f of x. So I'm going to have cosine of f of x times dx of, instead of this one here, I still have f of x here. And looking into this here, my f of x was something that was interesting here, that earlier on we realized that actually our f of x was just y. So here I'm going to have cosine of y times dx of y, and because I have dx of y, this is just the same as just dy dx. So basically what this thing is saying is this. I am going to open this room here. So what this thing is saying is this. I'm going to take this out. I'm going there. So what this thing is saying is this. This is going to be equal to y. Let me use the green. I have y plus x times dy dx plus this whole thing here. We know that actually it was just cosine of y times dy dx, as you can see it here, and then this whole thing must be equal to 2x. And then what I'm going to do here, I'm just going to add a new page after. So this page is just saying that I'm going to take this y to the other side, so I'll be left with everything that is x dy dx, plus cosine of y dy dx, because this one is going to the other side, and then I'll be left with 2x minus y, because it was positive, that side is going to be negative. I'm going to factor out dy dx here. I will end up having dy dx, and then once I take it out, I'll be left with x plus, and then once this one is taken, I'll be left with that one, which is cosine of y, and then on the right hand side I still have 2x minus a y. And then I'm going to divide on both sides by this thing that is inside the brackets, so I'll end up being left with dy dx is going to be 2x minus y all over x plus cosine of y, or just if you want to start with this, but I still think it's fine, so you stop there. So that's how you factor, you differentiate implicitly. So that was one of the questions that we actually had. And then now the next one was, what was it? We're in C, and our C was actually, let me clean this up. Our C was actually e raised to xy is equal to x plus a y. So basically, if you look into this part here, you will find out that even if you would attempt to make y the subject of the formula, you can't, because there is also a y there. So there's nothing that can be done to bring that one down. So it cannot come down and also deal with this at the same time. So to differentiate this, all you need to do, you need to differentiate on both sides. But before you do that, you need to realize that y is actually some function f of x. So y is a function in terms of x, but you can't make it the subject of the formula. So that's what you wanted to actually realize here. In other words, this function here is the same as e raised to x times f of x, which is equal to x plus f of x. That's what is happening here. And then in order for you to deal with this whole thing here, what you do, you just say, okay, I am going to have to take the derivative on both sides. So I want the derivative of e to the power x times f of x, and then take the derivative also on the right hand side of x plus f of x. So that is actually how you end up finding the derivative. So what is the derivative of this? I have that nice thing here that is sitting in the value of x, right? So I am going to let this thing here, because I know the derivative of some function, let's say some function h of x is equal to e to the power x, because the derivative is still going to be e to the power x. So instead of having an x in the exponent, I have x times some function. So I'm going to let this to be equal to u. So I'm going to say let u to be equal to x times f of x to deal with this, and then let some w. I usually say that let u equal to this and y equal to, but now y is part of this, so y cannot be used, so I'm gonna end up using w instead. W equal to, I'm going to replace that whole thing, so I will end up having e raised to u. So I'm replacing that whole thing by u, and then this derivative here is going to be the derivative with respect to u first. So I will end up having u, because this whole thing here is going to be in terms of u of w times the derivative with respect of u, but now with respect to the variable that we had there, which is x. So this and that will cancel out, and we're left with the w, and w is actually that whole function. So that is what is happening here. Let me redo this just in case you are not getting what I'm trying to say here. What I'm trying to say here, this derivative is going to be the same as derivative of w with respect to x, which is this x. But w is actually not in terms of x. That is why we just say, oh, this whole thing here is going to be derivative of w with respect to the variable which is u there. And then I am going to multiply this by the derivative of this new variable here, but now with respect to x. So that is going to be this part here. And then on the right hand side here, I will have the derivative of this, which is just going to be derivative with respect to x of x plus the derivative with respect to x of f of x. The right hand side I will keep it as it is because I'm still working on this side here. And instead of having this w here, I am going to actually change it and say that actually I know what w is. My w is actually e to the power u, and then d dx, and my u is going to be x times f of x. And then now I can move forward, and then the derivative of e to the power u with respect to u, we know that is going to be e to the power u, fine. And then the derivative of this, we have a function and a function, they are being multiplied together, so we need to use the product rule because we are multiplying two functions. So you keep the second as it is, and then you multiply by the derivative of the first, and then you plus, and then you keep the first as it is, and then you take the derivative of the second, right? That's what we do here, and then that's going to be a product rule. The derivative with respect to x of x, we know that is just a 1. The derivative of this, I want to keep it as it is for now. We will deal with it at a later stage. And then here I still have e, I have u. What is my u? My u here, I said my u is x times f of x, so my u is going to be x times f of x. And then inside here I still have f of x times the derivative with respect to x of x is still 1, I know that. And then now I'm left with this part here. I'm gonna have a plus here, I have an x, and then I still have the derivative with respect to x of f of x. This is going to be 1 plus the derivative with respect to x of f of x. Now, if we go back, I wanted to clean this part here, or I can just take this and then place it here, and then take this whole thing down there instead of wasting time. Yeah, I'm gonna keep it there, don't want to waste time. And then here, what was my actually f of x? My f of x was y, so I want to have my y back, so I will end up having here e raised to x times y. Inside here I have my y times 1 plus x times d dx. My f of x is just y, so I have dy dx, and then equal to, I have 1 plus d dx. My f of x is just y, so I have dy dx. And then what I need to do, I need to expand here, so I will end up having e to the power xy times y, so it's still going to be y, plus x times e to the power xy times dy dx equal to 1 plus dy dx. Of course, now I'm going to take this whole thing to the other side, and because it's positive this side, that side is going to be negative, and I'm going to take this whole thing, because it's positive this side is going to be negative on the other side. So if this one goes to the other side, I'll be left with xe raised to xy times dy dx, and then I'm taking this to this side, so it was positive, so it's going to be negative. Dy dx is equal to 1. This was positive, so in that side it's going to be negative. E raised to xy, and then I have a y there. And then the next thing that I'm going to do, I'm going to factor out this on the left hand side, so I have my dy dx, and then once this one is taken out, I'll be left with the x e raised to xy, and then once this one is taken, I'll be left with 1. And then this side I have 1 minus e to the power xy times y. I divide on both sides by this, and I'm left with the dy dx, which is just the same as 1 minus e raised to xy y divided by x e raised to xy minus a 1. So that is actually what we are actually ending up with when it comes to number 3. Hope you are following here. And then we are left with number 4. So what is going to be our number 4? So number 4 is saying differentiate each of the following functions using relevant rules. So we had our f of x, which was equal to 2 times 5 raised to 2x, and wanted to find f prime of x, which is just the same as, because the independent variable is x, so is d dx. And then inside we're going to have 2 times 5 raised to 2x. Because this one is a constant, we can always pull it in front, so we end up having a 2 times d dx of 5 raised to 2x. And of course I know how to take the derivative of 5 raised to x, because if I have a function of this kind, its derivative is going to be the same as 5 raised to x times ln of 5. But the issue that I actually have here, instead of having an x here, I have a 2x. So I'm going to let this one here to be equal to u, let u equal to 2x, and then I'm going to let my y equal to this whole function here 5, but instead of having 2x, I'm going to have a u, so that this is going to be 2 times dy dx. But my y here is in terms of u, so I cannot do that, so I will end up having du and then multiplying by du dx. And then what is my y? I am going to replace that. I'm going to replace my y here. So my y now is going to be 5 raised to u times du dx, and I'm replacing my u to be what it is, 2x. Now I'm going to end up having a 2. What is the derivative of this? Is going to be the same as 5 raised to u, because I have a u and u, times ln of this constant here, which is 5, times what is the derivative of that? Is going to be just a 2. Of course, this is going to be 2 times 2 is going to be 4, times 5 raised to u. My u was actually 2x, so I have my 2x here, times ln of 5. That's what we're actually looking for here. The derivative of this is going to be the same thing, and then you multiply by ln of this constant, and then times the derivative of the exponent, which is just a 2. That is why we end up having a 4. Let's go to the next one. The next one was our b. We had our f of x, it was equal to e to the power 3x. And we know that if our function was just e to the power x, we would know that our derivative is the same as e of x. But instead of having e of x here, I have 3x in the value of e. So I'm just going to say, let u to be what is sitting in the value there. So it's going to be 3x. And my y is going to be this function here, e. But instead of having this whole thing, I replace it by u. So that f prime of x is going to be dy dx. But now if you're looking into this, my y is actually in terms of u, so I want this to be dy du times du dx. And then I replace things here, so I'm going to have d du. Instead of y here, I have e to the power u, and then d dx, and instead of having a u here, my u is the same as 3x. The good news is that if I have a u and a u, the derivative of this is still going to be the same thing, and then the derivative of 3x is going to be 3. And of course I can just say this is 3 to the power u, and I can say that this is going to be 3e raised to u. My u was actually, what was my u here? My u is actually 3x, so here I have 3x. So that's how we are taking the derivative of this. This is 3x. And then we had our c here. Our c, we had f of x, and our f of x was actually equal to ln of, we had 2x plus 1. And then if you take a look into this, you will find out actually that we have this nice thing here, which is just saying that instead of having an x, I have something there. I know if I had h of x is equal to ln of just x, I would be able to take the derivative of this, because the derivative of this will just be equal to 1 over x. But now, instead of having an x, I have a function. So I am going to let u to be that function here, which is just 2x plus 1, and my y is going to be ln of what is inside. I'm replacing it by u, so that my f prime of x is going to be dy dx, because the independent variable is x. But if you look carefully into this here, my y is not in terms of x, it is in terms of u. So this is going to be dy du times du dx. So this will end up being there. We are using chain rule there. And then once you have this nice thing here, you can see that we will end up having d du, and my y, we know that it is ln u. And the good thing, now I have u and u. And then I have d dx, but instead of a u, I know that my u was actually the same as 2x plus a 1. What is the derivative of ln of u? Where we have a u there, we will end up having a 1 divided by ln of u. I mean, that's how you actually take a derivative of ln. It's 1 over x, but here we don't have an x, we have a u, and we have a u, so it's going to be 1 over ln of u times, what is the derivative of 2x plus 1? The derivative of this is going to be just 2, plus the derivative of a constant is just a 0. And now you are left with just 1 times this whole thing is just going to be 2 divided by ln of u. And our ln of u, we know that is going to be ln, and the u that we had, it was 2x plus 1. So we have 2x plus what did I do here? No, there's a mistake that I did here. Ln, the derivative of ln of u is just gonna be 1 over u. That's not correct. It's just supposed to be 1 over u, and then here we still have 1 over u, and then this one was just supposed to be u. We're supposed to replace u to be just 2x plus 1. That's how this is supposed to be, because they did, like I said here, the derivative of ln of x is 1 over. It's not 1 over ln, so it's 1 over x. So even here we're supposed to end up having 1 over u, not ln. So that's how we're supposed to end this particular problem. And then our d was, we ended up having f of x, and our f of x was log base 10 of x squared. And then once you have this, you know how to take, if let's say your function was just log base 10 of x, you know how to take the derivative of a log function like this. It was going to be the same as just 1 over x, which is this x, times ln of this base here, which is base 10. So that's what was supposed to happen. But instead of having an x here, I have an x squared. So I am going to let u to be what is sitting in the value of x, and then I say my y is going to be the same function log base 10 of, I'm going to replace that thing by u. I have a u. Then my f prime of x is going to be dy dx. But now my y is not in terms of x, is in terms of u, so we'll end up having dy du. Because I have this new du now, it has to be taken out by just doing the same thing of du dx, so that this is that and this one is that. And if you look carefully into this, I will have d du. Instead of having my y is going to be log base 10 of u, and then I have dx, and instead of having a u, I know my u is just x squared. So how can I take the derivative? Of course, the derivative of this log, because I have a u and a u, so I know that this is supposed to be 1 divided by if I have a log base, so this u is supposed to be there, and then I'm supposed to have ln of this base here, so I'm supposed to have a 10 there, and then times the derivative of this. We know that this is just going to be 2x, and if you look carefully into this, this is the same as 2x divided by u ln base 10. And what was actually our u? Our u was x squared. So this whole thing is 2x divided by x squared ln of base 10, which is just the same that I can take out this x, and one of these x is going to be 2 divided by x ln of base 10. I would say stop here, but someone who is more motivated might just decide, I'm just going to say this is the same as ln of 10 raised to x. It's not going to bring any new information. So I would say stop here, but if you get to this and that, this is still the same thing. Now let's deal with the last problem, and then I will let you go. This last problem is saying that this was actually E. It said that you had f of x, and f of x is equal to x to the power x. That is actually the problem that we haven't yet covered. But how can we actually deal with this? We know how to deal with so many of the problems that we have dealt with. But now, how do we deal with this? Take note of this. If, let's say, I have a function h of x, and h of f is equal to x to the constant. This n is a constant. It can be negative, I don't have a problem. It can be a fraction, it can be decimal, it can be anything as long as it is a constant. My h prime of x, I know that this is supposed to be n times x raised to n minus 1, because this is a power function. And if, let's say, my function is x is equal to, I have n, some constant raised to x, because this one is going to be an exponential function. Okay, the reason I'm doing this, I know that you are used to having an a here. I just wanted to have a relation. So if I have an exponential function of this is a constant raised to that, I know that its derivative h prime of x is going to be a raised to x times ln of this constant a here. I know how to deal with that. But now I have this problem here. I have x raised to x, in other words, an independent variable raised to an independent variable. How do I deal with that? This one is a power function. This one is an exponential function. But if you look into this, an exponential function is an independent variable raised to a constant. This is not a constant. So this one here is not a power function, right? And this one is not a constant raised to an independent variable, so it is also not an exponential function. So how do we end up taking a derivative of this thing here? One way to do this, we wanted to change this function to look like something of this kind here. But if we are doing that, what can we do to this function such that we can change it to be a power function, so that we can use what we know about power functions? Because you cannot say that the derivative of this, f prime of x is equal to, I'm going to bring x down, and then I'm going to have x, and then I'm going to have x minus 1. You can't do this. This is not equal to that, because this is not a power function. We only do this if this was a power function. And also at the same time, we cannot just say, oh, our power function is just going to be, going to look like this. We're going to have x raised to x like this, and then we'll end up having ln of x. We can't do that because this one is not a constant. We only do that if this was a constant. So how can we proceed to actually deal with this particular thing here? Actually, it's not that hard, because one thing that I told you is that whenever you have a log base a of x times y, you know that this is always going to be the same as log base a of x plus log base a of y. That's what we said. And we also said that whenever you have log base a of x divided by y, we know that this is going to be log base a of x minus log base a of y. We talked about this. And we also said that whenever you have log base a of x to the power b, we can always bring this one down here and say this is going to be b log base a of x. And then we also know that whenever you have log base a of x, this is just the same as log base b of x divided by log base b of a. We know these rules. Now, how can we actually end up rewriting this function using these rules without changing this function, but we're still rewriting it so that we can either use that or that? We'll see. Can we use this? We can't. Of course, we still, let me also add some few so that you can still remember everything. And we said that if I have an exponential function of this, I can always rewrite with a different base and say that this is going to be it's going to be e raised to ln of a to the power x, because this and that, they cancel out. That's what we said. Let me rewrite this because it's going to make us not see what I'm actually doing here. We said that whenever I have a to the power x, this is the same as base e times ln of a to the power x, or log base e, because ln is the same as log base e. So this is the same as that. We talked about this. And we also said that this whole thing is still the same as a to the power x is the same as ln of e raised to a to the power x. Still the same thing. So this and that, still the same thing, because ln and e, they always undo each other, and this can come down to be that. So we have these things here. Now, if you look into this, we don't have a product of two things here, so we cannot use that. And we don't have a division of two things, we cannot use that. But if we are actually using this thing here, we can see that we will end up having to take a log on the left hand side and take log on the right hand side, so that I can bring this x down. So this one here, this one cannot be used, this one cannot be used. So this one can actually be used to actually help us so that we can bring this x down here. But once we do that, we will be forced to differentiate on both sides using implicit differentiation. So if you are good with implicit differentiation, you can use this whole thing. But because implicit differentiation, most people they usually find it hard to actually grasp it for the first time or the second time. They need to keep practicing it until they can get to the point. So this one, if you are not good with implicit differentiation, we cannot use it. And this one, of course, this one cannot be used because we don't have a division of things, we don't have a base of anything, we cannot use this. We can either use this one. But if you wanted to use the rules that we have, this one here, we just need to rewrite this part and leave this one alone, so that we have y as the subject of the formula and then equal to something. So we can try and use this one or that one. If we are using this one here, we will have a chain rule if let's say we take a derivative on this side, we have something of this kind, we'll have to take the chain rule of this lane. And because when you're dealing with the inside here, you will find out actually that we don't have e to the power x. We will also have to take the chain rule within the chain rule. So we'll end up having to take two chain rules within this function. So this one here, if you are not that good when it comes to chain rule, so I would say that don't use this one because you have to take chain rules twice. So I'm saying I'm not gonna use this part here. But this one here, we just have one chain rule which is just sitting there, and I know how to deal with that nice thing. I will tell you why I'm saying we have one chain rule here. So we will end up using this part here only. So we have our f of x, which is equal to x raised to the power x. And if you take a look into this and we use this, this is the same as e raised to ln of whatever this thing is. Why am I not bothered that this is a constant? Is because e and ln, they cancel each other. They just undo each other, and then we'll be left with this thing which is the same as that. So I'm fine. And then secondly, when I'm actually looking into this rule here, when I have an exponent inside something, I have something raised to an exponent, I can always bring the exponent down to get that. So this one here is going to be the same as e raised to x times ln of x. What does that simply mean? I want to find the derivative of this function e raised to x times ln of x. Now, if you look into this, if this function was h of x equal to e raised to x, I know how to find the derivative of this. And the derivative of this would simply be e raised to x, still the same thing. But instead of having that thing here, which is just x, I have something sitting in the value of x. I am going to let u to be x ln of x. And now that I have this nice thing here, all I have to do here, I'm just gonna say now my y is still going to be this same function, but instead of writing that whole thing that is sitting in the value of x, I'm replacing it by u. And then f prime of x is just going to be my dy dx. And now my y is not written in terms of x, it is in terms of u. So this is supposed to be dy du. But du was not part of this. That is why I have to take the derivative of u with respect to x now, which was this x here. And if you look carefully into this, you will find out actually that you end up having du, but instead of y I have e to the power u, and then d dx, and instead of u I will end up having x times ln of x. And if you look carefully into this, you will find out that I have a u, and the derivative of e to the power u is just gonna be e to the power u. Fine. But if you look into this part here, you will find out that I have y is equal to x as one function, y is equal to ln of x as another function. So I have a product of two functions, so I'm going to use a product rule. And the product rule is saying keep the second as it is and take the derivative of the first, which is x, plus keep the first as it is, and you take the derivative with respect to x of the second, which is ln of x. So that's what you end up with. So I have e to the power u, and then this one here was just ln of x. It was ln of x. So I will end up having ln of x, and then the derivative with respect to x of x is the same as dx, which is the same as just 1, or just say we'll have a 1 times x raised to 0, which is 1. 1 times 1 is 1. And then I have x times, what is the derivative of ln of x with respect to x? We know that is going to be 1 over x. Simple as that. And then of course we can try and simplify here and see what we are getting. I still have e raised to u. Inside ln of x times 1 is still ln of x, and then x times 1 is going to be x divided by x. X divided by x is just a 1. And what was our u? Our u was just, what was our u? Our u was just x ln of x. So here I have e raised to x times ln of x, and then inside here I have ln of x plus 1. And of course here, if you look carefully into this, e to the power x times ln of x, whenever I have something in front of a ln, I can bring it inside and say that I have ln of x raised to x, and then multiply by ln of x plus 1. And then if you look into this, the natural log and e, they undo each other or cancel each other, whatever the way you actually want to call it. We will see that this and this will actually end up cancelling it out, and then we'll be left with that thing, which is x raised to x. And then inside here we'll end up having a natural log of x plus 1, and we have this. You can see how easy this thing is. Very, 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 very easy. What is important is that you need to remember the log rules to actually deal with this thing here. I hope you actually understood what we're actually doing here. The lesson was very long, and hopefully you took some breaks in between. And then now what we'll actually look at, how we can actually use these derivatives to actually solve some of the other derivative problems that we have. So I'm just gonna stop here for now, and then we'll proceed in the next lesson.